So now let's proceed to the step response or the complete response of a parallel RLC circuit. So applying KCL at the top node, we have IC plus IL plus IR equal to I. IC can be expressed as C dV over dt, and we have plus IL plus IR can be expressed as V over R is equal to I. Expressing the equation in terms of IL, we have to remember our VL just equivalent to V because all components are in parallel. So expressing in terms of IL, we have L times C, second derivative of IL plus IL plus L over R times DIL over dt equal to I. Dividing the equation by LC, we have, if you look at this equation, this is the same differential equation with the natural response, but the term at the right hand side is a non-zero term. We have alpha equivalent to 1 over 2RC. We have omega naught equal to 1 over square root of LC. We express the equation in terms of V. We have C dV over dt plus 1 over L integral of V dt plus I naught plus V over R equal to I. So differentiating both sides, we have the derivative of V respect to time plus 1 over L V plus 1 over R dV dt equal to 0. Dividing this equation by C, we have 0. So this is just the same equation as the natural response of a parallel RLC circuit. Now, since we are talking about the complete response, so if we take the IL of T, is composed of forced response plus the natural response. Or for V, we also have the forced response plus the natural response. Solving for IF or VF for the forced responses, we treat the circuit as a steady state circuit, or we have T approaches to infinity. So this is at steady state. For the natural response, so for IN or VN, so depending on the roots of the characteristic equation, we have three equations. We have A e to the S1t plus BE to the S2t, so where S1 and 2 is equivalent to negative alpha plus minus square root of alpha squared minus omega naught squared. So in this case, alpha is greater than omega naught. So the circuit is overdamped. Now the next case, we have AT e to the st plus VE to the st, where S is equal to negative alpha. In this case, our alpha is just equivalent to omega naught. Or this is the critically damped circuit. For the last case, we have AE to the negative alpha t cosine of WD t plus VE to the negative alpha t sine of WD t, where S1 and 2 is equivalent to negative alpha plus minus J square root of omega naught squared minus alpha squared. Where this term is equivalent to 4 omega d. For this case, our alpha is less than omega naught. Or this is the underdamped case.